another very common conditional programming construct that's supported in VHDL is the case statement. All right. So here's what we'll do. Let's look at just the format of this, and then let's do a VHDL simulation and see how you actually use it. Okay. So what you do is, number one, the rule. You have to be within a process. Okay? And a case statement acts almost exactly like an if-then statement. It is a series of Boolean expressions that are evaluated, and if they are true, you make a signal assignment. Okay? So if you look at this, what you do is the keyword is case, and then you put the input name. And the input name is going to be whatever the signal is that you're going to make decisions based off of. Okay? Then what you do is keyword is, and then after that you use a keyword when, and you list in here all of the values for the input that you will evaluate. As it goes down here, it will, the first one it sees, it will evaluate, and then it will end the case statement. So once it evaluates it, you put this equal and then greater than, representing that you go over here and you do these sequential statements. Now you can have as many sequential statements as you want. You can have a bunch of them, or you can just have one. But these sequential statements are going to sit over here, and they will be evaluated when this choice is true. Okay, there's one subtlety with a case statement. The input name can only be a single variable name. Okay, see, you can't, if you had like 3 inputs, A, B, and C, you can't say something like case A and it would B and it was C, or A comma B comma C in the base model of VHDL. So the typical way that you do it is you always concatenate. If you have multiple inputs you want to look at, you concatenate them together into a new signal or variable name, then you use that to look at. Okay. The other things that you always have when you have a conditional statement is an others clause or an else clause, like in an if-then. It's the thing that handles all the other cases that weren't explicitly listed. Okay? So in this situation, you have this when, and then there's a keyword others, and that handles everything else. Okay? And then, of course, you can do end case to end the thing, and then you're done. And then there's some little neat tricks that you can do also, but it'll be better to show you in a VHDL simulation. Okay, so let's go ahead and fire up a simulation. So I'm going to go into my project folder that we're using here, and let's say new folder, and I'm going to do the date, and then I'm going to call this case. Okay? And what we'll do is let's just do our traditional System X where we have a 3-input combinational logic circuit. The test bench, I'll just grab that from our if-then example. So I'm in here, case. And I fire up Model Sim, and I didn't close my project from last time. You always should close your project. So what I should do is come into here and say close project. Yes, close. All right, so I'm back at Model Sim. I'm going to go create a new project, file, new project, and let's just call it project, and I'm going to browse to my new little folder called case. Okay. I go ahead and say, okay, you want to add a file? Yes, I do. I want to add my test bench. Then it says you want to create a file. I say, yes, I do. I want to create the system in that building. So I'm going to go System X. All right. Now, I knew it was called System X because I've been using this test bench a couple times, but if I didn't know that, I'd double click on the test bench, and boom, there it is. Here's the test bench. I look at it. I come down. What I really care about is this component that I declare in the test bench, which is what I'm going to look for. And then I have my component instantiation, and this is calling the design that you're designing. And then you can kind of notice that the test bench is driving in signals into your system. And then what we'll do is we drive in all the inputs. We'll use a waveform to observe the output. All right? Okay. So now I'm going to come into System X and start designing. First thing I want to do is, just so I don't screw up anything, I always like to come in here and I always like to copy this part. That way I get the spelling of the system right and I get the port definitions correct. So I'm going to copy this, and then I'm going to come into System X, and I'm going to start this puppy up. So entity, paste, and remember the is. So I come in here, I go System X is port. I have 3 inputs, A, B, and C, and then I have an output F, and I'm going to end entity. Got it. All right, let's fire up our architecture. So architecture, let's call it System X arc of System. System X is begin, end architecture, And I should be able to compile. So I save this puppy up, and let's go ahead and compile all just to warm up the compiler. All right, we're good to go. Now we can start entering functionality. So I'm going to come down here, and first of all, we need some functionality to model. So let's see if we have our little piece of paper here. And let's get a combinational logic circuit that you would like to model. So the inputs are, there we are, A, B, and C. You want to do a truth table or a min-term list?
Min-term list.
Oh. Just get that, let's make that guy go away. Okay, all right, so we're going to do a min-term list where, min-term list, why'd they even ask? It takes so much room. I'm joking. Min-term list is fine. Min-term list, I'm going to list the rows associated with an output of a 1. This has 3 inputs, so that means there's 8 codes. And the question becomes, what rows would you like to be asserted? 3? One of my favorite rows. 6? 7. I knew you were going to say that. 3, 6, and 7. Okay. Oh, I get it. Does everybody see that? Oh, it's too much. It's too much. Okay. So I come along to you, and I'm going to do the following. I'm going to start up a process. You have a choice whether you want to name the process or not name the process. Usually when you have multiple processes, you name them. You don't have to name them, but it's good practice. So I'm going to call this process system X underscore proc. Okay? Then what I do is I put a colon, and I do keyword process. At this point, we need a way to tell the process how it's going to trigger. Okay? You're either going to let it trigger immediately by putting nothing, or you're going to have it trigger based on a sensitivity list. Whenever you build real circuitry, you use a sensitivity list. And that's because that's how circuits work. Circuits work based upon events or signals. Okay? They don't just fire immediately. They're always based on something that's happening. So a sensitivity list is always used for synthesizable logic. Okay? And that's great because the sensitivity list triggers, you make signal assignments, it ends, the signal assignments are then implemented, and that's a real circuit. The alternative to that is to let the process trigger immediately and then come down inside of the process and use a wait statement. The wait statement suspends the process, and the signal assignments that have been queued are implemented. A wait statement is never synthesizable. Wait statements are only used when you do test benches or stuff that is only used for simulation purposes. So that's a key thing to keep in mind. If you want real circuitry that you're going to put on a chip, it has to have a sensitivity list. So we're building a real circuit. So what we're going to do is come in here, and I'm going to list all the inputs. The reason that I list them, so I'm like on decision number 2. Decision number 1 is, do I need a sensitivity list? This is a real circuit? Yes. Decision 2, is this a combinational logic circuit or a sequential logic circuit? If it is combinational logic, which is what we're designing, we list all the inputs to the circuit in the sensitivity list. Okay? So in this situation, the inputs are A, B, and C. If it had been a sequential logic circuit, we would have only list signals that would have triggered the device. And that's almost always clock and reset. Okay? All right. So we got our system, we got our process, we got our sensitivity list. I come down, and I'm going to go down here, and I'm going to say begin, and this is going to begin my process, and I'm going to come down here, and I'm going to do case, and I'm going to now put in here the input name that I'm going to look at. Immediately, I can't do this because my inputs are called A, B, and C, and they're all scalars. They're all bits. Okay? So I only get one variable name here, or one signal name. I have a choice. I can create a new signal up here. I can create a signal, and then I can concatenate my inputs together under this new signal. But a process is kind of neat because we have at our disposal a variable. So to keep everything clean, why don't we just button this up within the process? That's usually how you try to do it. Process is also good because it's almost like it bounds your functionality so that it's like a little segment that you know what it does, and it's easy to debug if you don't let it get too big. So I'm going to come in here, and I'm going to create a variable. A variable. Now I'm in side of my process. This is my process, and it's going to come all the way down until I end the process, and I'll just put it there just to show it. And I'm going to declare a variable. Declarations always come before the begin statement. That is true if I'm doing a signal declaration. The begin would be the architecture begin, but now I'm doing a process declaration. That's within or before the begin statement within the process. Okay, so this is where it would be. I'm going to declare this variable by typing keyword variable, turns red, and now I need to come up with a descriptive name. Do you have a name you would like to use?
ABC.
ABC, almost like you're following along in the textbook. Okay, ABC, and I'm going to give it a signal type. I'm going to create a 3-bit vector, and then I'm going to concatenate my signals and assign it to this new thing. Okay, so I'm going to call this bit vector, and we're still using bit and bit vector. These are the standard things that are built into the VHDL standard package. We'll stop using those very rapidly as we move into more advanced packages. But I got my bit vector. I'm going to call it 2 down to 0. And that now is 3 bits wide. I can initialize this if I want. If I wanted to initialize it, I could do this. I could say 0, 0, 0, but I don't really have to. I'll just put it in there for no reason. Okay, I have my new variable, and now what I want to do, I did that so that I could assign my inputs ABC that are scalars over to this variable, and I could use that single variable name as the argument for my case. All right, so here I go. I'm going to assign to a variable ABC. Do you remember the assignment operator for a variable? Is this it? No. Is this it? Yes. That's the assignment. It's a colon equal. All right? Now I'm going to assign to it. I can still use the concatenation operator. A concatenated with B, concatenated with C. And now I got it. All right. Now I'm ready to do some casing. Come into here. My variable that I'm looking at is case. So I say case. ABC is. And now I'm going to list the Boolean conditions for ABC that I will look at, and if evaluated true, I will make a signal assignment. Okay, so here I go. I'm going to come into here and I'm going to say when ABC is equal to 0, 0, 0, I am going to do these assignments over here. I'm only doing one assignment, so all I got to do is simply put that. So when ABC is equal to 0, 0, 0, this will be evaluated true. It will make the assignment. F gets assigned to 0, and then it will be done, essentially. It will only do one of these. Now, how do I end my case? We'll list all those input conditions, but if I wanted to end my case, I got to do this, end case. All right, so now at this point, all I'm going to do is list out each and every input code. And you know that we always start like this just to show that this is how you would do it, even though you know that there's faster ways, especially when you use the win others. But I'll show you that in a second. Okay, so I'm going to pop down. Let's do the first 4 rows, and then I'll change the input codes. 1, 0, 1, 1, and I'll update the outputs here in a second. So let's grab these now. Boom, 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 boom. All right, so just to separate, I'll put a space for now. I come over to here. I go boom, 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 boom. All right, here we have it. When 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And now what I got to do is I got to update the outputs. So I want the output to be asserted when the input code is a 3. Okay? So which one of these binary codes is it?
That one.
The one I'm highlighting? Fantastic. So row 3 is a 1. Then I'm going to go down here, and I'm going to say row 6 is a 1, row 7 is a 1, and I got it. In this situation, I'm going to make this a little tighter. In this situation, I have listed each and every possible input code, so I don't need another's. Okay? But this is very short-lived. As soon as we change to different data types for our signals and signal vectors, we're going to need to always use the win others. But for this one, let's just not use it and see if it works. Okay? All right, so I feel pretty good. Let's see if our compiler agrees. Did we forget any colons, semicolons, is's, else's? Compile, selected. Oh, feels good. It's green. It's green on screen. Oh, but does it simulate? That's all that said is that you didn't have any syntax errors. Now let's go check to see if it actually did what we wanted. So I go to my library tab. I go to my work directory. I double click on the SystemX test bench to load the highest level of my simulation. Okay? I want to see the highest level because I want to see the stimulus. I want to see the inputs being driven into my device under test or what I'm actually designing. So I come into this guy. I go into my objects pad or objects tile, and I right click. I say add to wave signals in region. When you do region, that gives you the top level, all the signals at the test bench level. Okay, it doesn't dig into underneath. Okay, so I got A, B, C, F, and they're all underscore test bench. I know that this simulation's running for about 800 nanoseconds. I go ahead and pop that in there. I go run. I'm zoomed all the way out to the very end of the simulation. So I click and I hit F for fit. And look at this. Yeah, you can kind of tell it's looking good. But immediately what I want to do is I want to take these input scalars and I want to combine them into a signal. I want to combine signals. Let's call it ABC. I'm going to call it ABC Vec just to make it different from what's in the design. And I say OK. And now here it is, 000001. Once I have that as a bus, I delete my input scalars. And I'm looking at it and I'm like, oh, this is pretty nice. Yeah, but you know what would even be nicer? Why don't we change these into unsigned decimal so that we can actually see the rows that are associated with the true. So let's change this radix to unsigned. Oh, baby. 3 is asserted, 6 is asserted, 7 is asserted. Bam. Okay, life is good. You know what's kind of interesting? Let's do this. I want to go, let's add to wave signals in design and see what kind of stuff that I get here. Let's see here. Not much. All I get, let me restart the simulation and I'll run this. Up here I get F underscore TB all the way down to ABC underscore TB. Notice that the big difference is that the signals that I see when I add all the signals in the design are everything diving down into your DUT, okay, or into what you're designing. So notice that it's called DUT because that's how the test bench instantiator does, but you'll actually see the signals A, B, and C, and F as their original names within your System X, okay? That becomes important when you start doing internal signals. Notice that the variable isn't here, is it? It's not there. That's fine. That's just because it's not a signal. All right, but anyway, this is pretty cool. Let's go back to this, and now let's look at making the case statements way, way easier, okay? So I come back to here. The first thing I want to do is say, let's use an others clause, okay? I want to use an others clause in order to pick up the rest of them. So let's list a couple that are explicitly an output of 1, and then let's use when others to pick up everything else. To prove to you that it's real, let's do a different one. So let's go F. Let's change the logic to, what do you want to do?
1.
Just 1.
Well, I'm letting other people put in some inputs.
No, it's 261. I like that idea. Here's yours. Anybody else want to do it? So first of all, you would never do this. This is stupid. Why did I even do it? You put them in order. So it's 1, 2, 6. I got carried away with the course numbering, okay? I'm only human. All right. So now I'm going to have rows 1, 2, and 6 assert. So here we go. I'm going to come over here and I'm going to say, all right, life is good. Let's see. All I'm going to do is say, let's go to the first one. When row 1 is on the input, the output is asserted, okay? Then, and I realize I could get these below, but I don't know. I'm just copying and pasting. Then I go when row 2 is the input, the output is asserted. And then when row 6 is the input, the output is asserted. Then what I want to do is I'm going to nuke all this stuff, and I'm going to say, to handle all the other cases, I'm going to come in here, and I'm going to do when keyword others, and then I make that final assignment, which covers all the other input codes.
Yeah, it should be 110. Yeah, 110.
Oh, yeah, absolutely. All right, look better? All right, well, let's see if this works, okay? So I'm going to come over to here. I'm not going to end my I'm not going to end the simulation. I'll just recompile and restart it. Okay, so I'm going to come back to the project, and I want to compile this to get the new logic in there. Then I'm going to come over to my waveform, and what I want to do is come up to here and hit restart. That'll clear it out and load in the new compiled version of my logic, and then I'm going to hit go. Ah, look at this. We got 1 is asserted, 2 is asserted, 6 is asserted. Bang. We did it. All right. That was a little easier, wasn't it? That was a little bit easier. Here's the one that's even easier. Okay? Here's what I'm going to do. You can actually, for similar outputs being f is equal to 1, you can actually pipe delimit input codes. And this gets you all the way down to a 2-liner. Okay? So let's check this out. First of all, let's change our logic so that we know it's a real thing. So let's do another one. What do you want the logic to be this time? 1, 2, 3. That's fine. All right, 1, 2, 3. So I'm going to come back in here, and here's what I'm going to do. I'm going to say when 1, and all I do is I pipe delimit the inputs. Now, pipe delimit that's the pipe, and all I do is I simply list, so this would be 0, 2, and then I do pipe, and then I go 3, and there it is. Okay, so let's see if this works. So I got this. I'm going to go over to here. I saved it. I got to compile again. Compile selected. This is really off the screen. So I compile selected. Let's get it on the screen so you can see it. Okay, it looked like it worked. Let's go back to waveform. Let's go ahead and restart the simulation, and we'll see what we got. So I come over and I go restart. Yep. And I'm going to go run. Ah, look at this. 1, 2, 3, bang. Worked. So you have 3 methods to do this. Okay? Which one do you want to use? Whatever. They're all the same, right? They will all synthesize into the exact same circuit. But that is the case statement, and it's very handy. It's actually a lot of times what you'll see is when you need to list out a lot of input codes, case statement is better. When you only have like 1 or 2 input codes, an if then seems to be better. Okay, so that is the case statement.